Hi guys, this is Mrs. Gastler, and in this video we're going to talk about springs. So you've probably done a lab in which you looked at what happens to a spring when you hang a mass on it and then some more mass on it. And hopefully you saw that the more mass you hang on it, the farther it goes. And that shouldn't have been surprising at all. That phenomenon was first discovered by this guy named, I think, Robert Hooke. But he called it Hooke's Law because that's what people like to do. They name stuff after themselves. And the formula that he wrote down was the force that the spring uses to pull that mass up to keep it from falling down, to balance out gravity, right? Because gravity is pulling this thing down and this thing down with more force. The spring has to pull back up, so that force from the spring, that's what we're comparing here, is proportional to the distance that it goes. And there is some factor there. And this was probably a little bit confusing because we use K in those formulas that we write down, but and this is actually a K. This K right here is known as, I thought I had another colored pen over here. I don't. Okay, we'll just use this. Ooh, a pencil. How about that? This is the spring constant. Okay, it's not just any old constant, it's a spring constant, and it tells you a little bit about the spring. And the X is the distance that it has stretched from rest. And so the farther we stretch it, the bigger the spring force is. You could actually feel that if you took the spring and you pulled it this way, you would feel that I have to pull harder to stretch it harder. And it works with all kinds of elastic things. And then there's that negative on there. Now the negative comes from the fact that, and hopefully you can see that from my diagram here. So we have this, like, there's that rest. And you can see here that we have stretched it this way. Can you see how our X and the F are in opposite directions? And our X and our F are in opposite directions there. That's why we have a negative, because that X is a vector and that F is a vector. And there's an alarm going off. There we go. Those things are vectors, and because F and X are in opposite directions. Now what you need to make sure you don't do is that you don't go in and stick a negative in the X to make up for those opposite directions. What we're really kind of doing is just marking those as X. Whenever we write these down, they don't usually have that negative in there. I'm sorry, they don't usually have the vectors in there. We're just recognizing that they are vectors, okay? So F and X are in opposite directions. Okay. And so that's what it looks like. And these pictures are when they're at rest, but we could look at them anywhere they are in there, and interesting things happen. Okay. So the next thing we need to do is we need to look at what happens. So this is the force of the spring. That's it. Okay. So what happens what other things can we look at when we're thinking about what's going on with the spring force? Okay. And the next thing we want to look at is, well, how do we find out how much work was done by the spring or how much work was done on the spring? And because we're in AP Physics 1, and some of you might have some calculus skills, but many of you don't because you're not taking calculus yet. And you might someday in the future, but we don't have the ability to do something. So if we were taking calculus-based physics, we would know that work is the integral from the initial position to the final position of f dx. But we don't know what to do with that in algebra, okay? And so that doesn't mean anything to us. So we would put some question marks over there. Yeah, we don't, what do you do with that? Okay, so in algebra-based physics, the way we have been doing this and the way we've done this so far already is when we have a varying force, when the force varies, the work is found by finding the area under the curve. Do you remember that? Okay, work is the area under the curve. And hopefully you found in your lab some sort of line like this. Okay, now this was actually probably the force that you were pulling with. And then later on you stuck a negative in there, realizing that what you were measuring was the force of gravity and that there really needed to be a negative in there. And that's totally okay. And so you had some initial distance and some final distance that you were pulling from. And this is an integral, and that's what an integral is. The integral is finding the area under the curve. If you wanted some advanced, or some pre, what do they call this, a trailer? Yeah. Okay, so this is an integral, and it means the area under the curve. Okay. Well, our curve here is a flat line. Well, no, it's straight. It's a straight line, but it's not flat. So when we find the area under this curve, what we're looking for is this. That is a shape. Now, you've probably taken geometry because you had to have geometry before you took AP Physics 1. How do you find the area of a triangle? Well, if you remember, that's 1/2 base times height. Okay. Now we were just talking about how to find the force at any one of these heights here. So to find the force here, the maximum force. So let's see, the height of this triangle would be this one here. So that would be this force here is that force there. So let's see, what is that? That would be minus k. That would be that force is k times xf. Okay, so that's our base. I dropped the negative because that's not what it looks like on my graph here. And then, whoops, that's the height. I switched those. Okay, and then my base is going to be xi to xf, and if I started from my relaxed position, then that would be 0. And so I have xf as my base, so xf is right there. So when I'm finding the work, it's 1/2 base times, base times height. And if I simplify this, I'll have 1/2 k xf squared. So however far I stretch my spring, that's how, and the spring constant right there, that's how much work I did. So when we write this down, though, we can drop the xf and understand that we're however far I pull it to, and I can just call that x squared like that. So that's the work done by the spring. Okay. Now the work done by the spring, the next question is, well, how much energy does my spring, can my spring hold? So if we're doing, let's talk about the signs really fast. Signage, okay. Is it positive or is it negative? That's a really important question. This really depends. So remember that work equals FD cosine theta, and that's the formula that we used when you had a constant force. For a constant force, okay. Our force isn't constant here, but using this cosine theta will help us think about whether or not it's a positive or a negative. Now, in our situation, our forces are either in the same direction, and if our mass is going up and down, our forces are either in the same direction or they're in opposite directions, okay? If our force is in the same direction as the displacement, if the spring is pulling the mass up, then the work is going to be positive. If the force of the spring is pulling the mass up, okay? So if it's below that rest point and the mass is pulling it up, then it's going to be a positive work, okay? But if the force of the spring is pushing, okay, the spring is, if we've compressed the spring, the mass, and it's pushing it back down or something like that, then it's going to be negative. And so it's going to be constantly changing how much work it's doing, whether it's doing the work or not, on the mass. So this is going to be doing the work. Spring does work, okay, on. And so you just have to think about what's happening and whether you're talking about the object or the spring, and who's doing the work and who's getting the work done on, to think about what's happening to the amount of work and what's happening to the energy, okay? Speaking of energy, let's talk about that next. It's elastic potential energy. Sometimes people call it spring potential energy. If you call it elastic potential energy, you'll understand that it's the same kind of thing, whether it's a spring or a piece of elastic or something that is stretchy. It's the same situation. We use the symbol US, which makes more sense to call it spring potential energy. And if you'll recall, we'll come at this one. So work is the change in potential energy. And in this situation, it's a change in spring potential energy. So if my potential energy goes from the final, if I'm going from some initial position to some final position, then it'll be XF minus 1/2 KXI. And you can see that I leave the F there. You can see that the spring potential energy is 1/2, we'll leave that up there, 1/2 kx squared, okay, to be moving that one. And so that's our formula right there. So when you're looking at the potential energy in a spring and any other energies that might be taking place, this is the one for the spring here. When we start talking about the mass on a spring that's exhibiting simple harmonic motion, all sorts of fun things are going to happen, and it's totally fine, okay? You have some questions to answer in AP Classroom, and I think the textbook if you want to do those. Let me know if you have questions. Thanks for watching.